Hello, hello, hello. So today we're going to follow on with our irrotational flow discussion, and we're going to talk about the Laplace equation and how to get numeric solutions for the Laplace equation. So the objective of today's lecture is to simulate irrotational flow within an arbitrary geometry. You know, a lot of what we've done before, the theoretical solutions or the analytic solutions, you can see where we're beginning to get limited by the geometries themselves, right? If we're going to try to do complicated airfoil shapes like we did last time, doing that theoretically is going to be difficult. All that displacement, putting vortices everywhere and all of that. So really the way forward, as opposed to doing those transformations, which I think is what was really being done before computer simulations came into fruition, the way forward is to do computer simulations. So we'll set up a domain over which we'll solve the Laplace equation, and we can impose boundary conditions, either within the domain or along the edges of the computational domain. So that's what we're going to talk about today, arbitrary geometries and the solution to the Laplace equation. So what we're going to do is reintroduce, I'm going to start with the Taylor series expansion because that's where it always starts with computational solutions. And then I'm going to show you how we can discretize the Laplace equation using Taylor series expansions. Then we'll discuss boundary conditions and some marching techniques and some solution techniques associated with putting it all together. And then finally, I'll show you a solution for flow over a forward-facing step. Now, as an add-on to this module, I'm going to do another computational module where I take you through the numerics. So it'll be after this one, and it will include how I actually discretized and programmed both Matlab and Fortran. So I wanted to introduce you to Fortran at this time. So anyway, we'll get started. So the numeric solution to the Laplace equation, there's the Laplace equation there. Del squared psi is equal to 0. And let's solve this over a computational domain. So the idea is that we have some computational domain, some xy space, and we're going to discretize it. So we're going to convert it to a solution that's not over x and y, but I and j. And so we call x and y the real domain, and we call I and j the discrete domain. So the independent variables x, which is smooth and continuous, can be represented by I, which is discrete, times dx, which is our resolution, right? So in this case, we could take, for the example that I showed you, x is going from 0 to 1, and I is going from 0 to 5, right? With a dx of 0.2. So 5 times 0.2 is 1. The real difference between x and I is that obviously x is continuous. It has values like x equals 0.5. And for the discrete domain, I is only an integer, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. And there is no solution at I is equal to 0.5. All right, so it's the same in y. And so you can discretize the y direction. And you can use a different dx dy. There's nothing that says that you have to use the same value for the resolution. And so, as I mentioned, this is called the real space, and the ij space is called the integer space. So this is the real space xy, and this is the integer space ij. So we'll switch back and forth. Now, the dependent variables, psi, they will have solutions in the xy space, the real space, and we're going to assume that they're equivalent to the solutions in the ij space. Really, I suppose this should be approximated by, right? Not necessarily equal to, but approximately equal to what the continuous solution is. So we only have the solutions, the discrete solutions at the node points here, whereas the continuous solution is continuous everywhere, right? Okay. So some comments. Numeric solutions do not provide a continuous solution. I think I've beat that home. Numeric solution is just an estimation, right, to some order of accuracy that we'll discuss. So any kind of solution you get from a computer, like CFD solution, computational fluid dynamic solution, it's just an approximation to what the actual solution is. And in general, I think you should be very skeptical of any kind of computer solution. There's these beautiful codes these days, and you launch them, and they have all these drop-down menus, and you click on this, and you click on that, and you know, it generates these beautiful plots. But in general, I would always be very skeptical of any kind of solution that you get. The odds that the first solution you get is the right solution is basically zero, right? So it takes a lot of checking. It takes a lot of work to get a good numeric solution for a flow field, especially a viscous time-varying flow field. Okay, so let's review the Taylor series expansion. To me, the Taylor series expansion is one of the coolest ideas in all of mathematics. I love the Taylor series expansion. And Taylor here is not the same guy as G.I. Taylor, different Taylor altogether. So the Taylor series expansion is the idea that if you know everything about a function at location x, all of its derivatives, so you know its value, and you know every derivative, the derivative of the function with respect to x, the first derivative, second derivative, third, and so forth, then you can make a prediction about the value of the function somewhere else. So here's the idea, right? If I know the value of the function at x naught, and I know its first derivative evaluated at x naught, and I know its second derivative evaluated at x naught, and so forth and so on, all the way out to all the derivatives, then I can make some prediction about what the value of the function is at x1. I mean, think about how cool that is. That says that if I know everything about this instant in time, if I know what the value is of every particle on the planet in the universe at this instant in time, and what its time rate of change is, and what its second derivative is, what is that, the jerk, the third derivative, and so forth. That means I could make a prediction about every particle in the universe at some future point in time. That's pretty amazing, right? I mean, really, that's kind of godlike, right? So I really enjoy the idea of the Taylor series expansion. All right. So in order to illustrate this, we've been through this review before, but it's just so wonderful that I can't help but do it again. So let's consider a function, sine of x. Here's a plot of sine of x. And let's consider a point x naught to be pi by 2. And what if I wanted to know the value of x1 at pi by 4? So that's easy enough, right? If I know the value of the function sine, then at x naught, the value of sine is this 0.7071. And if I wanted to know the future value of pi, can I predict it with a Taylor series expansion? So if I know the value of sine, then I can just plug it in at pi by 2. Sine of pi by 2 is equal to 1. So that's if I know the function, right? And of course, if I know the function sine, I know the future value or the spatial value of sine going out forever. But let's use a Taylor series expansion to approximate it, right? Can you calculate the value of y1, or I should say at x1, can you approximate the value of y1 at x1, knowing only information at x naught, right? So the answer is yes, that's a Taylor series expansion. And so the first term expansion, if I just said that that I'm going to predict x1 here, and the way that we build up the solution is we say f of x naught plus the first derivative, and so forth. So the one-term expansion would just be, well, the value at some future value is my current value, right? That would be, say, the dumbest approximation I could make. So the value at x1 is approximately the value at x naught, 0.707. Well, that's not such a great approximation. What if we used a two-term expansion? What if I said the value, the future value, or the value at x of 1 is equal to my current value plus the derivative times the distance? And so you know what the derivative is. It's the slope locally, right? So really what you're doing is you're making a linear approximation to the value x1, right? So plot this function. So there's what the function looks like. My two-term approximation, you can see it doesn't look anything like a sine wave. It's basically a linear line, or it's actually cosine x is the slope, times x2 minus x1. So this is the spatial variable. So really, it's a linear approximation, right? This is the slope right here, cosine of x times the independent variable, x1 by x2, that's the distance, plus an intercept, right? So it's a linear approximation, that's the two-term expansion. And so you can see that the approximation for this, I can calculate what cosine is at x naught. That's my slope, and I multiply it times that distance plus the intercept, which is sine pi 4. It's up there. So I'm approximating the value here, which is around 1, exactly 1, by this number up here, which turns out to be 1.262. So the two-term approximation is slightly better than the one-term. I mean, the one term is off by about 0.3, and the two term is off by 0.26, so it is a better approximation. You can also see it's exhibiting this behavior where I'm under-predicting for an even number, for an odd prediction, and over-predicting for an even number. So I expect when I go to a third order, through a three-term expansion, that I'll under-predict the real solution, but to a closer degree, right? All right, so the three-term expansion looks like this. So I'm taking the first three terms. I can take the first derivative of sine. I can find the second derivative of sine and evaluate it locally to make a better prediction about what this function looks like, right? And when I do that, I get this 1.044. So I'm honing in on what the solution looks like. What about a four-term prediction? Under-predicted, so 0.987. I'm getting pretty good here. I'm plotting what the functions look like so you can see what they look like. All right, now it seems kind of silly, the first time I saw this, because sine, I have to know the function in order to generate the Taylor series expansion, right? But really, when you do numeric solutions, you don't know the function, but you do know all the derivatives. So that's the power in that we're going to use the idea that we can solve for the derivatives and use those derivatives in a future step in order to make future time predictions or future space predictions. I keep saying the word time, but really it's time or space or whatever the independent variable represents, right? Okay, so that's the Taylor series expansion in all of its awesomeness. The theoretical solution is y equals sine x, and the simulated solution, so all computer solutions, we're going to use this to solve the Laplace equation or any kind of CFD code or finite element code, are based on some sort of discretization, most likely based on a Taylor series expansion or something close to a Taylor series expansion. And most are first or second order accurate. So first order is really that two-term solution, that linear solution, and second order is that one that's a parabolic solution. So that's it. I mean, to find a code that is any higher order than second order is really difficult to do. And most of the times, most computer codes that you run are first order because they're fast, right? The hope is that your mesh, your computational domain, is so dense that you're going to resolve derivatives to some high degree. But that's why you should be skeptical. I mean, these things are very rough approximations of what the real function is. All right. So in order to get started with discretizing the Laplace equation, let's talk about how to build up our stencil. So let's look at a first order approximation, or I should say a Taylor series approximation of the function psi. So there it is. It's really all I did was just replace the previous Taylor series expansion with the variable psi. This is a forward difference, meaning that if I want to predict what some future x value is, or some greater x value, then like pi by 2, I can predict that with this linear slope, and I get a prediction like we talked about before. I could also do a backward difference, right? So I don't have to always have a positive delta x. I could have a negative delta x, and that's really giving me a prediction about what's already happened, or some x less than pi by 4 value. And so when I do that, I just change the sign here, and every other, because this is odd and this is even, the signs are changing. And so the Taylor series expansion, the backward Taylor series expansion, just has a sign difference in there. But ultimately, you're getting a prediction about some value lower than pi by 4, so that could be, say, x minus x equals to 0. Now, I've also introduced this half of an integer time step. You'll see why that's important, not time step, discretization step. So I said that integers have to, this I has to be an integer, but you could think of it as I prime, or some half integer spacing. That's not really a problem. What's going to happen is when we go second order, that's going to go away anyway, so you'll see what's going to happen. So I have this forward and backward discretization, or Taylor series expansion, and if I rearrange them, I can basically solve for the slope, right? So where's that in the previous slide? Let's see. Here's the slope right here and here. And so what we're doing is I'm just going to move this over to this side of the equation, move this over to that side of the equation, divide by delta x, and we'll arrive at something that looks like this, right? So now I've got an approximation for the derivative at I, using information about the value of psi at I plus a half, and its current value at psi at I, plus a whole bunch of stuff, higher derivatives at the current location. So that's the forward difference approximation for the derivative, not the state variable, but the derivative. And I can do the same thing. Yeah, all of these terms are known as higher order terms, right? First order accurate, meaning in delta x, the lowest value of delta x that appears is delta x raised to the power of 1. So this would be considered first order accurate. And you can see this is just a slope, right? This is just the value of psi, where I'm at, plus the value of psi at a distance delta x away, divided by delta x. That's just saying that the derivative is equal to the slope of the value of psi. Super simple approximation. And it's basically assuming linear behavior, right? Because it's first order accurate. If I include the higher derivatives, it would be higher and higher order accuracy, but I'd have to know all of those derivatives at my current location. All right, the backward difference is very similar. You just rearrange what was on the previous slide, and you solve for the value of psi at I minus psi at I minus a half divided by the distance. So that's, again, a linear slope. And you've got a whole bunch of higher order terms that augment that approximation. So if I add these two together, right, if I just simply add these two and then divide through by 2, I'll end up with this. So if I just, remember old school adding of polynomials, you just add this and you get that, divide it by 2, so I move the 2 over, and then add these. You see if I add these two terms, what's going to happen? This and this are going to cancel, right? So I just get psi at I plus a half minus psi at I minus a half divided by 2 because I had 2 of these. So I move that 2 over there. And then these terms are added. Something beautiful and wonderful happens. This first term is negative. The second term is positive. They're exactly the same. So they drop out. I lost that second derivative term, that delta x order accuracy term, but the rest of these stay. So every other one should be gone, right? Now notice that if I again looked at the order of accuracy here, I would say that the order of accuracy is delta x squared, right? So if delta x goes to 0, then the order of accuracy goes to 0. But in general, these are first order accurate solutions, forward and backward difference approximations, and the central difference is second order. And it's not very costly for me to get that second order accuracy, which is why a lot of computer codes use second order accurate approximations. To get third order means I have to actually carry that information about this derivative here, which isn't that big of a deal, but it's just computationally more expensive, and everybody wants their code to run fast. So a lot of times you'll get second order accurate. And sometimes you'll have the ability to click on some function. We're talking about GUIs here within a CFD code to get that higher order accuracy. All right. So what does that mean? Well, think about some function of psi at some location I here. And we're approximating the derivative, right, which is the slope. So you can calculate the slope, or if you knew exactly what the slope is, here you can kind of visually see what the slope is. And when you do this with your eye, you're including information about points far, far away, right? And so really what that means is that when we do this first order, second order approximation in the Taylor series expansion, I'm using information just about from this data point and this data point to make an approximation of what the slope is. I'm not using information further out. That's higher and higher order approximation. So when you look at the function and you draw the slope in there, really you're visually using information about what the function looks like away from that location. And in fact, that utilization of information is a higher order approximation. So the computer is dumb, and it doesn't even know what the function looks like between these 2 points, right? The computer just knows this value and this value and this value, and it's trying to make an approximation about what the slope is. And it's trying to not only make an approximation of the slope, but the first derivative, second derivative, third derivative, and so forth. Anyway, here is the function psi, and I have drawn on there the exact slope of the function at that location. So we have to take the derivative and evaluate it there. But when we do numeric solutions, we don't know what that derivative is, so we approximate the derivative by just using what the values of the function are, right? So in a forward difference, right, I'm just using information about this node and this node. So it's a straight line. So I'm saying the slope is this straight line. Now I've extrapolated it beyond those 2 points so you could see it, but you could see that the forward difference approximation of what the slope is not that great, right? I mean, it's not horrible, but it's not that great. Backward difference means I'm going to use information about this point and this point to approximate the slope. So it goes directly through those 2 points, or it goes exactly through those 2 points, but it's a straight line through those 2 points. So you can see that's the backward difference approximation. Now, both of those are first order accurate. The central difference is second order accurate. It uses information at this location and this location in order to approximate the slope. And so second order accurate, this is typical of second order accurate schemes. It's using information, more and more information. And as I mentioned, if you went third order accurate, you'd be using information about this point, this one, this one, this one, and this one. So you're using more and more information to make an approximation at that location. You can have second order forward differences and second order backward differences, and you use those a lot of times at the boundaries, but I'm getting ahead of myself. So anyway, I think that's clear as to what's going on here with this first and second order accurate approximations for the slope in a forward, backward, and central difference scheme. All right, so now let's discretize this Laplace equation. And so here I've written out the Laplace equation in terms of its xy coordinates. And let's isolate the derivatives, right? So let's pull these derivatives out, this operator. So I just have the first derivative here, right? And so I know what the discretized approximation for the first derivative is using central difference, so I can plug it in there. That's from the previous slide. So I'm approximating this derivative and this derivative using our central difference second order accurate approximation here and here. And then I expand this. So that I then operate on each one of these. So I FOIL this out and operate to get this. And notice I've got a derivative again. So it's a derivative at the half node locations. So then I can use the stencil again at the half node locations. And you can see what's going to happen. When we did the first order derivative, we needed information at the half nodes, at I plus a half and at I minus a half. And here, we're taking the derivative at I plus a half. So now I'm going to need information at, let's see, I and I plus 1. Right? So then when I get the second derivative, I'm going back to the discretized mesh again. So it looks something like this, right? So this derivative right here is this term. This is this term here. So it's using information at I plus 1 and at I in order to make this approximation for what the derivative is in the x direction. And then over here, we're doing the same thing. I'm using information at j plus 1 and at j in order to make some approximation as to what the derivative in the y direction is. And it's the same for these other terms. So I have all of these derivatives together. So this is all now just in terms of psi. And you can see that I have psi at I, j. It appears here, and here, and here, and here. So I can rearrange and solve for the value of psi using its neighbor values. And if I let delta x and delta y equals to 0, the denominators all simplify and cancel. So I end up with this really tight formula here, very simple for what the current value of ij psi is using its 4 neighbor values, 2 to the left and right, and 2, 1 above and 1 below. All right? Cool. So I have the Laplace equation in its continuous form, and then I have the discrete version of the Laplace equation that we're going to solve for numerically. Now, the way that this worked out, right, was because of I selected central difference and blah, blah, blah. But you could select higher order terms, or you could use only forward differences or second order forward differences, whatever. There are a zillion schemes out there in the literature about how to do this discretization. This isn't the only way to do it. And whatever you end up with here is called the stencil. So you'll see that word in the literature. What's the stencil? What stencil did you use and so forth. So this is a very simple stencil that really is just a grid point, right? It's a plus sign where I'm using information about the top and the bottom and the left and the right to make a prediction about the intersection of this plus. So that's what we mean by kind of a plus stencil. All right, so knowing the value of your nearest neighbor nodes, we can approximate the value of psi. So here's this stencil, right? That's what it looks like on our grid. Here's our XY grid, and we're going to apply all of this. We're going to apply this function to solve for the interior nodes using this derivative. Now, what we're lacking here is boundary conditions, right? So we have to specify what the boundary conditions are at the edge of our domain. We're only going to use the stencil, the discretized, to solve for the interior part. The boundary conditions are going to stay the same all the time. I mean, that's what boundary conditions are, right? They are the solution that we impose onto the Laplace equation. Back to the musical instrument analogy, you know, a guitar can play whatever song you want as long as you apply proper boundary conditions to the string. How you can find the string on the fretboard and how you pluck the string. Both of those determine what the string actually plays or what solution the string gives you. It's the same in this differential equation bit, right? We can find the boundary in order for the Laplace equation to give us that particular solution. So this is the stencil here applied to some central node. And notice that when I go to calculate this node right here, it's going to use information at that boundary, it's going to use information at this boundary, and then it's going to use a neighbor that's inside the central difference scheme and inside there. So the stencil there, right, is overlapping with the boundary conditions. So it's pulling information from the boundary conditions, and then you can see this node right here would use part of that and part of that and part of this and part of this. So the solution will propagate into the domain, right? And so what we need to do is we need to iterate this stencil and reapply it over and over and over to this boundary so that the information has time to propagate in and kind of come to equilibrium. So this is iteration. It's not time iteration, right? This is a time invariant problem. This is, you know, way back when we derived the Laplace equation. It's a steady solution, right? I guess really it says nothing about the irrotational flow. Says nothing about time, but when we got del dot v is equal to 0 for incompressibility, we assumed that it was temporally invariant to density. So there is some constraint on time here. So this iteration, don't confuse it with marching forward in time. The in-between steps as we march towards the solution have no physical significance at all. Later on in the course, when we do more numeric work, you'll see how we can correct all of this. All right, so let's talk about the boundary conditions. Basically, we can apply, this is a second order solution. We're going to need two boundary conditions, one in space and one in, two in x and two in y. So that's 4. So here we're applying 4 along the edges, so to speak. And the boundary conditions that we can apply are we can just specify what the value of psi is, that specifying the value of the stream function or specifying the value of the state variable. That's a more general word for whatever the variable is. That has been named a Dirichlet boundary condition after Johann Dirichlet. And if we specify the gradient, then that's called a Neumann boundary condition, specifying the gradient along the boundary, named after Carl Neumann, who was a crazy great mathematician, Carl Neumann. So you'll see his name all over the place. Anyway, so we have to either specify the value of psi on the boundaries, or we have to specify the gradient of psi on the boundaries. What about initial conditions? Well, make a good guess, right? That's basically what we're going to do for initial conditions. If you know kind of what the flow field should look like, you could kind of put in the stream functions that you think, In general, I just set them all to some constant and hope for the best. All right. This idea that I touched on the previous slide where we march through the domain and information propagates through the domain is called an explicit scheme. So we're solving for this value of psi using these neighbor values, and we kind of march through the domain in order to do that. That's an explicit scheme. The opposite of explicit is implicit. And an implicit scheme is we write all of these equations. We write this equation at ij, and then we write the equation at its neighbor at I plus 1 j, blah, blah, blah. And we write this whole thing, all of these equations, and then we simultaneously solve that system of equations by doing a giant matrix inversion. That's an implicit scheme. So in one, quote, iteration, boom, you get the exact solution to all of those algebraic equations, right? I'm not going to do implicit schemes here. I'm going to do explicit. And even when we go into doing time-varying viscous flows, we're still going to stick to this explicit marching. And it's pretty common in fluid mechanics. I'm not sure why that explicit schemes dominate the field, although you'll see some implicit CFD codes out there. And for whatever reason, in finite elements, often it's implicit codes dominate and explicit codes are kind of secondary. All of this that we've done here is called finite difference. And if you do this in 3D, it's a finite volume sort of calculation. But there's a little more to the finite volume. Really, the finite volume is over an integral, and you discretize the integral, and it's more stable. But this is the first, historically, this was the first thing that was done, so I'm showing you finite difference. All right, so that's explicit. That's what marching means. Your initial guess, if you have a really crummy initial guess, you might converge to the wrong solution. And remember, wrong solution, that would be maybe the solution you don't want. But it could be a solution, right? The Laplace equation, as you have seen, has many solutions. Flow around a circular cylinder, or even the building blocks, vortexes, sinks, and sources. So if you guess really poorly, it might converge to the solution that's close to that guess, but it might not be the solution that you want. And you'll see some of that in the project. You have to be careful to kind of guide this solution or pick a good enough initial condition that you'll converge on the solution that you want. So this marching is really, is you start somewhere in a corner or wherever, and you kind of begin with a node, like you begin here with a node, and you calculate that node based on the stencil and its initial guess, and then you march through the domain as I'm showing here. Calculating each node sequentially using the values, the current values of psi of its neighbors. So this sort of little movie here is very much exactly what you're doing here. Notice you're not calculating on the boundaries, right? The boundaries, once you set them, they should stay that way for all time. Now we've just marched through the domain, and so what you would do, that's one iteration, is you would start over here and you would march through the domain again, and you would continuously do that until the difference in psi no longer changes. One way to monitor that is just to take the difference in psi from one time step, or one iteration I should say, to the next. And as that goes to 0, all those differences squared and summed up in the square root of that, as that difference goes to 0, your solution converges. All right, so now I thought we would do an example. This is a picture of Healy-Shaw flow over a forward-facing step. So the flow is moving here from left to right, and it's going over this step. As you can see, the streamlines bend and go over, and this would be a nice, fun flow to simulate. You can see that the boundary conditions appear that there's evenly spaced streamlines along the inlet, so that implies that it's constant flow, right? The difference in the streamlines here appear that's constant flow. Now you can see where the streamlines get tight together over a distance, that there's a lot of flow here, that the velocity is fast. So basically all of the flow bound in this region looks like it's squeezed into this region. So of course it's incompressible, so it must be going fast there in areas of high gradient. And then far away, the streamline looks fairly unaffected, right? It's kind of flat there. And the distance between streamlines does not appear to be changing, so that means the velocity along that flat streamline is constant. So we can apply a boundary condition of constant inflow here along the inlet, a single value of psi along the top, and then a value of psi along the bottom. That would be the streamline, or the kind of the stagnation streamline that represents the body. It's not really a stagnation streamline, but it represents the body. And then some gradient of velocity on the output side. Does it appear to you that these lines are the same? Same spacing. If so, then that would be constant velocity. All right. So we discretized the domain here, and this is kind of arbitrary. I just say, well, I'd like to have 10 computational nodes in the I direction and 6 computational nodes in the J direction, and I start with 1 here, so it's 1, 2, 3, 4, 5, 6. That's because Matlab, in its infinite wisdom, is not zero relative, which drives me crazy. So you can't specify an index to an array in Matlab of 0. I don't know what they were thinking. But so we're stuck with this one relative thing. So it's a very coarse domain, right? If you think about what that would look like. But it's simple to see and to carry forward, so I'm gonna do that. So as I mentioned, we're going to just specify a linear inlet here. So that means an even distribution of the value of psi. And so just arbitrarily, I'm picking, starting at 0, 0, 1, 2, 3, 4, 5, along the inlet. And since I picked this arbitrarily, started at 0 and counted up to 5, and these don't have to be integers, right? They could be whatever. Then the top is going to be set to a psi value of 5. The outlet, I need all of the flow that goes in needs to come out, right? And so really, if you remember what the value of psi is, the actual value or the difference in values represents the flow rate. So I have a flow rate effectively of 5 meters squared per second, or 5 meters cubed per second. That's a flow rate per unit meter into the board. So I need then to have the outlet go from 0 to 5. And because I have 1, 2, 3, 4 nodes here, I need to evenly divide this up. So I'm going psi is 5 by 3, 10 by 3, 15 by 3, so that this becomes a value of 5 here, right? That's 5, which matches this streamline along the top. So there's no problem. Now, along the bottom, I started at 0, so this will be the 0, 0, 0, so that all matches along the bottom. So I'll just specify along the step the value of psi to be equal to 0. And then when we march through this, I just won't march through this section of the block right here. I just won't calculate that. All right, so this is an example here. This is in Matlab. It's actually Octave. I say Matlab, but I'm using Octave a lot because it's free, right? And you don't need a site license for it. So if you learn to use it now, you can use it for the rest of your career. And it's just like Matlab, really. So let's see here. The solution procedure will march through the domain. We're going to use that explicit solution. The domain size is a grid of 6 by 10 or 10 by 6. I initiated everything to 0. Actually, I think that's a typo. I initiated everything to -1. So all of the domain is set to -1. And then I set the boundary conditions. And then we're going to march through. As I said, after this video, I'll show you the code and how it runs. We'll look under the hood here and see how it works. So the reason you're seeing this is a movie, and I'm going to play it here, but before I play it, I wanted to kind of talk about why it looks the way it does right now. This is Matlab's attempt to draw what the stream functions look like, right? So Matlab knows that the values along the boundary are equal to 1, 2, 3, 4, or 0, 1, 2, 3, 4, 5, and that's 5, and so forth. So you can see these are labeled. It's doing a good job. I mean, obviously it's going to draw that contour. It's the psi equals 5 contour. What else would it draw? And then it knows what the values are here. But because everything in the interior is -1, it's making an approximation. And so it's thinking that, well, there's got to be a huge gradient from -1 to 5. So it kind of like brings them all up and does this. You know, it's nice that Matlab is trying to curve fit this for us, but be careful about what Matlab shows you. This bit right here, this make movie, this will be more relevant when I show you how I did this. But really, this is a command line. ffmpeg is a command line command that you can download. I'm a big fan of using the terminal and command line and using Linux basically. So this is the command I used to generate this movie. And I'll show you that later. These are very powerful tools. All right, so here's the video. And what this is it's showing, after every iteration where I march through the domain, I'm showing you the solution. And I'm showing you the solution. So I can't remember if this is the 0th iteration or if this is the first iteration, but you'll see it improve. So this is each iteration, how the solution improves. And it's looking better and better. And I think this is just the first 20 iterations, although I iterated out to 100. But after about 20, with your eye, you can't see any difference, so I didn't plot them further. Now notice, it's not that smooth, but it's a very coarse mesh, right? So it's drawing kind of, if you look here to here, it's drawing a straight line, and of course that is, because that's all the data there is, right? What else is Matlab going to do but kind of draw straight lines, linearly interpolate this function so that it can draw a line between there. But in fact, there is no solution between there, right? So Matlab is just trying to guess what that solution is. And it doesn't always do a great job. I mean, that is a square right there, but it guessed over there. So it's drawing this 0 contour over there. It doesn't like to do squares. So this is the kind of the converged solution, if you will. And really the underlying solution is better than this because Matlab, we're subject to not only what the mesh is, but what Matlab contour plotting plots for us, right? And so I'll show you, if you really want to see what the solution looks like, this is it right here. This is the solution where the interior of the step is still set to this -1. That's what I set the initial condition to. And then you can see I imposed, here's my boundary condition. There's the psi 0, whoops, the psi 0 streamline right there. Here's this boundary condition. Across the top is the 5. And then over here is where we squeeze the flow from the inlet to the outlet. And so you can see that Matlab is not giving, it's not truly representing this solution because this point right here, right, is 0. Thank goodness, because that's what we want it to be. But Matlab instead drew this line over there. So Matlab does this, and whatever, you just have to live with it. So you can see the whole thing on this 6x10 mesh. But what if we wanted to increase the resolution? So if I increase the resolution by 10 in each direction, which is really increasing the size of this computation by by 100, then the solution looks much smoother. Matlab does a better job of doing, the curve fit, and it looks beautiful. There's a little bit of wonkiness here. Not sure what's going on there, but I think it's a plotting thing. And then I have to take more iterations as well in order to converge this solution. But you can see the streamline values that I've labeled. 0 is here, that's the step, and then a streamline value of 0.1, which is very close to 0, kind of follows along. So here is the original solution, experimental solution, and let's superimpose the irrotational solution. So you can have a look at it. You can see the streamlines. It does follow the streamlines pretty faithfully. It seems like in this region it's not doing such a great job, right? Some of that could be a result of, I just dropped this on there and tried to stretch it to make it fit. But it's pretty cool. I like this point here that it makes, that this is rectangular flow over a plate. The analog faithfully simulates the unseparated, meaning there's no separation, potential flow into the stagnation region of a concave corner. So in here, where it slows down, the stagnation region, and the infinite velocities over an outside corner. I guess it means like over here where it necks down. The water takes much longer to travel through the system if it follows a streamline, but passes through the stagnation region. This allows for greater diffusion of the dye, which is seen by the slight blurring of the streamlines. Yeah, that's kind of cool, right? If the flow is really slow right here, where the velocity, right, where the streamlines become the change in streamlines becomes very small, then any particle that goes in there that's carrying this dye, the dye can diffuse in a direction perpendicular to the streamline, and so the streamlines become fatter, or they look fatter than in regions where it's just zipping on through, and then the diffusion is less. That's kind of a cool feature of this flow visualization. So again, even though it's an experiment, it's not an exact solution because the streamlines don't get fatter there, right? We know that to be the case. So there's always, we can always complain about any solution, experimental or simulated. All right, so that's the end of this talk, and I guess I'll see you next time. All right.